This problem is from MIT Integration B 2026 finals. So this is the first problem of that competition. One of them, total 5 questions were there. This is the one of them. So now the question said that we need to find the integral limit n approaches infinity, integral 0 to 1, summation k is equals to 1 to n, 1 upon nx square plus kx plus n dx. So this is the problem. And now the first step will be to just interchange the summation and integration sign, and just for simplification purpose, and this will not affect this problem because we are integrating with respect to x and the summation is on n and the limit is on n, so interchanging them will not affect the original problem. So yeah, I have interchanged that. I have taken the summation outside and integration inside. Now I will try to simplify it first. Now this is the standard. In the denominator we can make it in a perfect square form and try to take it to somewhere of tan inverse at like 1 upon under root a square plus x square in that kind of form. So this is the standard technique, so you may be familiar with it. So I will just try to make it a perfect square by just plus and minus k upon 2n square. I am taking a n outside, 1 upon n. Why I am doing that? Because of course there is a multiple trial of that, but the gist of it is that n is approaching infinity, or if I can have a 1 by n outside, so it will help me in the later stage when I can just approach it to 0, so when putting the limits. So that for later stage, but for now this is the way to do it. X square plus k upon n x, or also you can just try to make coefficient of x square unity for simplification purposes. So yeah, trying to make the perfect square here, this plus k upon 2n square, so this will become the x plus k upon 2n ka whole square, plus we have we will combine this one with this, so we will get 4n square minus k square upon 4n square. Just take the LCM, simple as that. Okay, now the another step will be that we have reached here. We have get to a form of a square plus something, we can make it as b square by just under root of something and whole square. We can write it as under root of 4n square minus k square upon 4n square ka whole square, just like that. Or we can just for the purpose of making it as a square plus b square, we can write this as under root of 4n square minus k square upon 4n square ka whole square. So just basically I am writing this as a as square of under root ka a ka whole square. This is what I am doing, just for the purpose of making it a square plus b square form in the denominator, so that I can take the integration as tan inverse x. If you know the integration of tan inverse x, that is. Yeah, now the next step will be, as I said, I will write this as something like that. Just a is this value, this whole value is a. Now I hope you got the gist of this method. Now limit n approaches infinity, these all things are same. I am just, what I am doing is I am writing it as 1 upon x square. If you take this as x and this as b, so it will become as tan inverse of this whole thing. X plus 2 k by 2n will be treated as whole x, and for this we will have under root of this, so under root of it will become nothing but under root of 4n square minus k square, or niche mein we will have 2n, because under root of 4n square will be 2n. So this 2n will come in the numerator, and this under root of 4n square minus k square will come here, because as you know that if you try to integrate 1 upon a square plus b square, some form of that, and this is just a function of x, a is a function of x. Okay, so you can write it as a tan inverse of a, and b will 1 by b will come here. Okay, and of course if you have some coefficient of x on a, that will also come here. The basic integration, I hope you are familiar with it. So that what I am using here. So I have written this as tan inverse of x plus k by 2n, and that 2n came on here from here, and upon under root of 4n square minus k square, and then I am putting the limits 0 to 1. That is that. Now again, if you move forward, you can see that this n cancels, I cancel it out. So from here I got the idea of taking the n common, so now you can understand it. Of course this not comes in just a single go, I need to try it multiple times. That's how I get to the method. Now again moving forward, 2 upon under root of 4n square minus k square and putting the limits, just put the values, so it will change it to this. Now don't get scared, I will here use a very beautiful identity of trigonometry. Tan inverse A minus tan inverse B is equals to tan inverse A minus B upon 1 plus AB. I like this identity very much. It's a personal favorite from the trigonometry. It just I happen to have used this identity in some very difficult problems that made, because yeah, now just move forward, let's move forward. I will not get into it. So this is just take it as A, take it as B, and apply the identity, then use the simplification A minus B upon 1 plus AB. This simple algebraic simplification is there. You will get to here after applying the LCM and doing this identity, you will get to here. Now in the denominator you can say this we have there, just take the LCM and do the summation. You will simplify it in the form of this will reduce to, you can see that k square will cancel it out, because we have minus k square, cancel it out. Of course you can see that here also we have under root of 4n square minus k square, and this will go in the numerator, so under root will cancel out. So that I have written here 2n minus k upon under root of this 4n square minus k square will remain here. This under root of 4n square came here, and on the numerator we have a 2n minus k, because if you simplify this it will get to 2n into 2n plus k, and from the numerator it can just write it as a plus b into a minus b. And just do it, just apply the identity, you will see it. I have just skipped some steps, and this is the rough calculation, that's why. And now moving forward, so I'm not focusing on here because this is the simple part. The trickier part comes from, I'm explaining the trickier parts. Now this simplifies to under root of 2n minus k upon 2n plus k. Now here comes the part, the trick where I was stuck for so much time. Yeah, most of them can come to this step. Most of the time I was able to come to this step, but moving on from here was the difficult part. So now if you see that I can't do much of anything, the limit or the summation, I can't do much, but I need to solve this identity, I need to simplify this thing, then only I can apply the limits and I can just solve the summation. So if you see 2n minus k upon 2n plus k, this part is which took me a lot of time. I am writing 2n minus k upon 2n plus k as 1 minus k upon 2n upon 1 plus k upon 2, 1 plus k upon 2n. So now if you see, this is sum of form 1 upon 1 minus a upon 1 plus a, and this reminds me of a identity in a trigonometry where I have something as 1 minus cos square theta upon 1 plus cos square theta, 1 plus 1 minus cos theta upon 1 plus cos theta, and I write it as 10 square theta by 2, as if you remember, or you may remember it as tan square theta is equals to 1 minus cos 2 theta upon 1 plus cos 2 theta. Maybe you will remember that identity. So just I am writing k upon 2n as cos theta, so it will become 1 minus cos theta upon 1 plus cos theta, that is nothing but tan square theta by 2. If you are familiar with the identity, you must be familiar with that, then only you can understand that. Now since I have assumed cos theta as k by 2n, and this has reduced to tan square theta by 2, so if I write it as this is tan square theta by 2, so under root of tan square theta by 2 will be tan theta by 2, and tan inverse of tan theta by 2 will be theta by 2, and theta is cos inverse k by 2n. So this whole thing reduces to what? Half of cos inverse k by 2n, half of cos inverse k by 2n. I have just done many steps in the air, so forgive me for that, please. Not a very big fan of neatness, in mathematics. So now this I have reduced it to half of cos inverse k by 2n. Again, not looking very good to me, because what do I do from here? Like n approaches infinity, so what? How do I simplify the summation? So if you see now, I'm gonna write it as so this is what we have currently. Now again I will just combine it and try to simplify doing some algebraic. I will just take 2n cos inverse k by 2n inside and then try to make it as k by 2n. So I will take 2n 4n square outside, so that, and after applying the under root it will become 2n and 1 minus k upon 2n ka whole square. So similar as numerator and denominator. Now I can see something, some pattern maybe, because I have k by 2n as common, and if you know the integration of cos inverse x, so it is a 1 upon under root 1 minus x square. So I think I may get somewhere. So but here also I got stuck. Now the step here also is a very tricky one for me, was a very tricky one for me. So here what I will do, I can see that in this summation what are tn or let's say tcat, kth term, what is the kth term in this summation. So kth term is if I assume if you can say that k by 2n and since k varies, so I will vary the tk, so it will get to 1 by 2n, 2 by 2n, 3 by 2n. Okay, so I am just writing k by 2n as tk for understanding. So I am writing k by 2n as tk. So difference of each term of the k plus 1th term and kth term in the summation will be k upon 2n, k plus 1 upon 2n minus k upon 2n, which is nothing but 1 upon 2n. So this is the difference of the terms that I have gotten into. So now as n approaches infinity, this tk will approach 0. So this is the very neat technique which I took a lot of time to come up with. I hope you understand it. This is a limits concept, so I may explain it later, but this video is getting long. So this become, if I write k upon 2n as t, k upon 2n as t, so it will become cos inverse t upon under root 1 minus t, as you can see here, k upon 2n as t. So this will become cos inverse t upon under root of 1 minus t square. Simple. Now you can see that for k equals to 1, t1 is 0 because n approaches infinity. For tn, n upon 2n, this is half, and n cancel out, so it is half. So limit will be 0 to half. Here this is the way to find the limits. Now the integral becomes minus of integral. I am changing the limits 0 to half. You understand now what I am doing here? Just I am converting the summation of k is equals to 1 to n approaches infinity, to an integral concept. I hope you are familiar with the conversion of summation to integral. I'm not going to explain that. That is a more of a fundamental concept. You must be familiar with it. So, and I am then for k equals to n and k equals to n, I am changing the limits from 0 to half, as I have find out here that t1 it is 0 and tn it's half. Well, it wasn't gonna be an easy problem, so of course I am gonna use some neat techniques here. Not easy problem here I am solving. So I is equals to integral 0 to half minus cos inverse t upon under root of 1 minus t square dt. So this is the intuition that I had earlier after watching this expression, that I may able to form it as a differentiation of cos inverse x as a 1 upon under root of 1 minus x square. Then I will be able to integrate it. So that was my goal. So from there all these steps came in my mind. I hope you understand. So just I am writing cos inverse t, differentiation of cos inverse t as 1 upon under root of 1. This is substitute as cos inverse t as a substitute p, and then it will become p dp. So the integration of p dp is nothing but p square upon 2. So that I am writing p square upon 2. That is now 0 to half is the limits. Just put the limits, of course. Then cos inverse 0 minus cos inverse half whole square, pi square by 4 minus pi. This is the correct answer. I hope you understood it, and the problem was very good. I will again show you the main problem. This was the main problem, and this is the answer that I got, and it is the correct answer. I have verified it. Thank you.